Welcome to the inaugural Giant Magellan Summit. Thank you for joining us today during International Dark Sky Week. I'm Dan Jaffe, president of the Giant Magellan Telescope. Over the next hour, you'll hear updates from our observatory from across the globe. This live stream is our opportunity to share progress and introduce you to the extraordinary people and institutions bringing the next generation of discovery to life. Before we begin, there are a few viewing and engagement options I want you all to be aware of. You can select your preferred language in the sidebar to your right. You can also actively participate by making comments, reacting to the updates you'll hear, and even asking questions. At the end of the summit, our chief scientist, Rebecca Bernstein, will answer select questions from both the pre-submission form and the chat as time allows. For those of you who aren't familiar with the Giant Magellan Telescope and the people behind it, we are a 501c3 nonprofit and the work of an international consortium of 16 leading universities and research institutions. Our consortium has more than 600 years of combined experience building the world's most powerful telescopes. My connection to this project goes back nearly 20 years. I served on its scientific advisory council, helped the University of Texas at Austin join the consortium, and led the development of one of the telescope's first-generation instruments, a near-infrared spectrograph called GMT-NIRS, which will revolutionize the study of planetary system formation, small stars, and other infrared objects. I'm truly honored and excited to now serve as the president of this remarkable observatory. As we look ahead, my goal is clear: guide the Giant Magellan Telescope through full construction in partnership with our international consortium, donors, and the National Science Foundation to ensure it becomes operational in the early 2030s, delivering world-class science for decades to come. And now, let's begin our program. We travel to Chile, where the skies are some of the darkest in the world and our future home is taking shape. Please welcome Oscar Contreras, Vice President and Representative in Chile, who will share the first update from the Giant Magellan Summit at our Las Campanas Observatory site.
Thank you, Dan. Hello, everybody. From the southern frontier of the Atacama Desert in the north of Chile, I welcome you to the site of the Giant Magellan Telescope. We're standing under the clearest and darkest skies in the world, just 2,400 meters over sea level and 170 kilometers away from the nearest city of La Serena. A privileged location on Earth that has established Chile and its northern region as the epicenter of astronomy and home to the majority of the world's ground-based astronomy research facilities. Once the Giant Magellan Telescope is complete, nearly 70% of the world's astronomical infrastructure will be located here. The observatory amplifies existing NSF investment in Chile, including the Vera C. Rubin Observatory, ALMA, and Gemini South. Three defining reasons explain why our country has become the best place for the development and future of astronomy: our unmatched environment, our unique southern vantage point, and a national commitment to science. The Atacama Desert offers not only some of the clearest, driest, and darkest skies on Earth, its high altitude, extremely low humidity, and a stable atmosphere create ideal conditions for observing the universe, with more than 300 clear nights each year. From the southern hemisphere, we also have a unique view of the cosmos. From Chile, we look directly toward the center of the Milky Way galaxy and into one of its spiral arms. This vantage point opens a window to some of the most compelling questions in modern astronomy, from search to habitable worlds around nearby stars to understanding how galaxies form and evolve. Here at our site in Chile, essential infrastructure is already in place, including utilities, roads, support structures, and the completed excavation for the enclosure foundation. We are currently in a strategic hall focused on completing and testing major components at partners' facilities across the world before building upward at the site. These components, including the telescope primary mirrors, mount, and science instrument, will begin shipping to Chile around 2028. We anticipate site construction activity to ramp back up in parallel as installation begin, which will employ over 200 people here in Chile. Chileans are very proud of the country's leadership in astronomy. This is not only defined by geography, but also its people and policy. Astronomy has become part of Chile's national identity. A recent national survey ranked astronomy among the top cultural identifiers for Chileans. The relationship of the Chilean people with the sky has long been a source of inspiration for great artists, including our Literature Nobel Prize, Gabriela Mistral, born here in Coquimbo at the famous Elqui Valley. Mistral wrote Noche Andinas, Andean Nights, in honor of these skies that shelter her. Our universities, our communities, and our government recognize the value of these extraordinary skies and have taken important steps to protect them. One of the most significant is the Chilean Light Norm, a national law designed to protect dark skies around astronomical observatories. While this regulation points in the right direction to strengthen Chilean regulation, it still needs further definitions that allow to face challenges ahead, to broaden the protection of this natural heritage of Chile, and with it the scientific and economic investment that astronomical projects represent. But protecting the night sky is an ongoing responsibility. As cities grow, industries expand, and development continues in northern Chile, we must ensure that light pollution does not erode the natural conditions that make this region unique. This is why the Giant Magellan Telescope has an active part and a strong commitment to preserve and protect dark skies. That's why we support the OPCC, organization that protects the sky quality of northern Chile, and Cielos de Chile Foundation, an initiative dedicated to dark sky protection, environmental stewardship, and science education. Together, we are helping inform communities, strengthen awareness, and ensure that Chile's sky remain among the darkest and most protected in the world. Because protecting the sky is not only about astronomy, it is about protecting an environment that supports scientific discovery, education, tourism, and economic opportunity for generations to come. It is also about connecting people to the universe. In fact, just this week we had the honor of welcoming the governor of Coquimbo region to our headquarters in Pasadena, California. The visit reflects the growing collaboration between regional leadership and the international astronomical community that calls northern Chile home. In a couple of days, at the Exploratorium in San Francisco, we will be announcing a new partnership with the regional government of Coquimbo. This initiative will help position the region as a gateway to Chile's world-leading astronomy and strengthen the connection between local communities and the global scientific discovery happening under these skies. We look forward to sharing more details very soon. We remain committed with the country's effort to protect these skies, advance in scientific discovery, and ensure that Chile remains as the astronomy capital of the world for the next century.
Thank you, Oscar. What you described captures why Chile is the world's astronomy capital, not only for the extraordinary conditions of the Atacama Desert or the number of telescopes there, but also for the nation's growing commitment to support astronomy for generations to come. I also want to highlight what Oscar just shared. Tomorrow, we will welcome the governor of Coquimbo to our offices here in Pasadena to celebrate a new strategic partnership. This collaboration will advance Chilean astronomy, support regional economic growth, and bring the excitement of discovery directly to the public. A press release with full details will be shared later this week. We received quite a few pre-submitted questions about Chile and the work happening there. To answer some of these, we reach out to experts within our consortium. The first question is especially fitting as it comes during International Dark Sky Week. Andrea, a Chilean journalist, asked about dark skies and what Chile is doing to protect them. To answer, we turn to Daniela González, Chief Executive Director of the Fundación Cielos de Chile and one of Chile's foremost experts on this topic.
In Chile, there is a growing momentum to protect our dark skies. On the public policy side, the government has reinforced the regulatory framework with the new lighting standard and better recognition of that areas that require special protection for astronomy. At the same time, scientific institutions, observatories, civil society, and local communities are working more closely together. Through the joint work between Fundación Cielos de Chile and GMagAO Corporation, we are advancing in an education and in public engagement program that is helping to build wider awareness about light pollution, because protecting our dark skies depends not only on regulation but on society understanding their scientific, environmental, and cultural value.
Thank you, Daniela. Our next question comes from Isabella, also from Chile, who is curious about synergies with other telescopes. To answer this, we turn to Adam Miller, an astronomy professor and AI expert at Northwestern University. He uses survey telescopes, including the Rubin Observatory, our close neighbor to the south, for his research.
Thank you for that fascinating question. Rubin and the Giant Magellan Telescope both are going to provide groundbreaking discoveries in and of their own right. But we're extremely lucky that both of these facilities are being built in the Southern Hemisphere and will be operating at the same time, because we can leverage them against each other to maximize their overall impact. Rubin is going to detect some of the very faintest sources we have ever seen in the universe. And what's especially special about that is that we're going to do it across the entire visible Southern Hemisphere. This means more than 30 billion stars and galaxies are going to be discovered by Rubin. To comb through all of that data, we're going to have to leverage all of the recent advances in AI in order to find the most spectacular, the most weird, the most wonderful stars and galaxies that are out there. And these things are going to be incredibly faint. So we will not be able to look at them unless we have the most powerful spectrographs in the world, which is what the team at the Giant Magellan Telescope is working on building right now. This will allow us to understand what is the chemical composition of the stars that we look at, what is the dynamics of the gas and the stars in the distant galaxies that we spy. And putting this all together will allow us to make groundbreaking discoveries, leveraging the impacts of AI, Rubin, and the Giant Magellan Telescope all at once.
Thank you, Adam, for your point about the critical role AI plays in synergies between our two observatories. We now travel back to the United States to take a closer look at some of the engineering and manufacturing progress happening now. We're headed to Illinois, where the telescope's massive mount is being built. To give us an update, please welcome Jeff Kimberly, CEO of Ingersoll Machine Tools.
Thank you, Dan, and congratulations again on your new appointment. Hello, everyone, and welcome to Ingersoll Machine Tools in Rockford, Illinois. I'm coming to you live from this huge telescope bay where there's a lot of exciting things going on. You know, for more than a century, Ingersoll has specialized in building some of the largest structures and machines in the world. Our teams work on everything from U.S. Navy submarines, spacecraft and satellite structures, giant automated fiber placement and 3D printing machines, and more recently, the most advanced ground-based telescope ever built. Our partnership with Giant Magellan Telescope began in 2016 and has grown into one of the most ambitious engineering and machining projects we've ever undertaken. To give you a sense of the scale, the telescope mount that holds and moves the telescope mirrors, instruments, and control system stands 39 meters tall. That's roughly the height of a 22-story building and weighs an enormous 2,600 tons. The telescope is so large that we had to build this new 40,000 square foot manufacturing and assembly bay, including a giant pit just to machine and assemble it. Next door to me is the largest 5-axis master mill gantry machine in North America, where we're setting up the first 3 semi-finished azimuth tracks to finish machine the key features, including the hydrostatic ways. Each of these enormous tracks weigh over 50,000 pounds and presents a challenge at every step of the manufacturing process. The fabrications themselves had to be flat within 13 millimeters from end to end. That's just over a half inch. When machining the azimuth tracks, we'll be holding a flatness to within 2/1000ths of an inch in the zone where the hydrostatic pads ride, and within 12/1000ths of an inch over the entire 70-foot diameter when the tracks are assembled. Then we're going to put this very large bearing assembly from in-place machining in the center. This arm assembly carries a turning head and a grinding head that will finish the radial and hydrostatic waste surface in place on the assembly floor. I personally have never seen this done before. I'm also looking at these very large earthquake dampening systems like giant shock absorbers and very large hydrostatic bearings, which are provided by our partners from OHB in Germany. These hydrostatic bearings allow this enormous mount to float on a layer of oil about the thickness of a human hair. That thin film removes friction and reduces vibration, which is critical when you're observing objects billions of light years away. Before this project is over, we will have assembled and tested the entire mount here in Rockford, Illinois, before it's disassembled and shipped to Chile. By taking on this project, we're maintaining and advancing the industrial base that our nation relies on. Looking ahead, our focus will soon shift to the final phase, which includes building the large C-ring elevation axis structure that allows the telescope to tilt up and down, building the huge Gregorian instrument rotator where all the scientific instrumentation will be located, building the massive primary mirror cell structures, and finally the very tall secondary mirror structures. This undertaking requires an incredible skilled team, and we're very proud to recognize key contributors across the U.S. supply chain, including Teledyne in Alabama, Dynasty Fabrication in Michigan, Steelwind Industries and In-Place Machining in Wisconsin, along with other partners across the country whose craftsmanship and discipline make this possible. This is one of the most extraordinary engineering projects in the world, and we are so honored to be a part of it.
Thank you, Jeff. What you've just seen is an engineering at an extraordinary scale, where a structure the height of a 12-story building must move with smoothness and precision of a laboratory instrument. The machining tolerances Jeff described reflect world-class precision manufacturing. We received several pre-submitted questions from our audience about the engineering behind the mount and the primary mirrors. The first question comes from Sarah, a journalist at Power and Motion, who's particularly interested in the hydraulics used for the mount. To answer this, we are turning to one of our in-house experts. Please welcome Keath, Senior Mechanical Engineer.
Thank you, Dan. Sarah asked a great question. The Giant Magellan Telescope structure incorporates two hydrostatic bearings that support the azimuth and elevation axes. These bearings operate by pumping hydraulic oil between an array of hydrostatic pads and a high-precision bearing raceway. Hydrostatic bearings were selected for the following key reasons. Number one, ultra-low friction. A constant, precisely controlled oil film separates the bearing pads from the raceway, resulting in ultra-low static and dynamic friction. Number two, high stiffness. The hydrostatic bearings provide excellent stiffness, both statically and dynamically, which enables extremely accurate pointing and stable tracking of celestial targets under normal operating conditions. And finally, an integration with an earthquake damping system. The same hydraulic system that provides oil to the bearings is also used to mitigate seismic damage to the telescope. This system provides vertical isolation and damping to the rotating telescope structure.
Thank you, Keath. That was a great explanation. Definitely one for the engineers in our audience. As Jeff mentioned in his update, the mount will ultimately support and control the heart of the Giant Magellan Telescope, 7 primary mirrors. These mirrors are cast at the University of Arizona's Richard F. Karras Mirror Lab, the only facility in the world capable of fabricating them. They are the largest optical mirrors ever made, each measuring 8.4 meters, or nearly 28 feet in diameter. And already 2 years ago, all 7 had been successfully cast, a remarkable milestone. Many of you had questions about our mirrors and their status, so we selected one from Chris in Arizona. To answer it, we're joined by Barbara Fischer, our primary mirror subsystem manager, who will give an update on our recent support system testing at the Mirror Lab.
Thank you for the great question. For those of you who may not be familiar with our primary mirror support system, it is designed to do much more than simply hold the mirrors in place. It operates with nanometer precision to adjust each mirror's position, compensate for gravity sag, stabilize its temperature, protect it from seismic activity, and maintain its exact shape as the telescope moves to track objects in the night sky. This system was tested last year at the University of Arizona using one of our completed 8.4 meter primary mirror segments. The goal of that testing, which was supported by the National Science Foundation Award to Reduce Risk, was to confirm that we can precisely control and shape the mirror to meet our specifications, including testing the temperature stability. The results were outstanding. The system performed as predicted, with extremely close agreement between our models and the measured data, maintaining stability and precision throughout. It exceeded our expectations and validated that we can successfully control the shape of the primary mirrors to the level required, marking a major milestone and confirming that this critical part of the telescope is ready to move forward.
Thank you, Barbara, for that update. As many of you know, advanced imaging, spectroscopy, and instrument development are essential to the transforming the light a telescope collects into discovery. Telescopes do much more than take beautiful pictures of the universe. A telescope is only as powerful as the instruments it feeds. Our instrument program is designed to deliver transformational science from day one and to grow over time as new technologies and science cases are developed. One of the most exciting examples is the Large Earth Finder, or G-CLEF, being developed by the Smithsonian Astrophysical Observatory and Harvard University. G-CLEF is one of the 7 first-generation instruments planned for the Giant Magellan Telescope and will help us explore planets beyond our solar system like never before. Next, we travel to Cambridge, Massachusetts to see this work in action. To explain how this instrument will change the way we study exoplanets and to provide a status update, I'm delighted to introduce astrophysicist Andrew Szentgyorgyi, the principal investigator of G-CLEF.
Oh, hey, thanks, Dan. I just wanted to say how excited we are here at CFA to be working with you and the GMT team to getting the whole telescope project, final design review level, so we can start building the GMT, in particular to start building the Giant Magellan Consortium Large Earth Finder, an instrument we're working on here at CFA to search for Earth 2.0. An Earth-like planet orbiting a star that's not the sun, and then to interrogate its atmosphere for evidence of biomarkers, evidence that there's life on the surface of that exoplanet. I just like to start with this picture because if an alien flew to the Earth for the first time, they'd look out their window, see this scene, and they'd know there was life on Earth. And they'd know there was life on Earth, not because of the glow on the surface of the Earth, from cities, that could be volcanic activity. It's this green glow that is the result of solar radiation bombarding oxygen in the upper reaches of the Earth's atmosphere and lighting it up like a neon bulb. And the reason there is so much oxygen is because photosynthetic processes cause plants to respirate oxygen and boost the abundance of oxygen in the Earth's atmosphere to 21%. If all the life were to abruptly end on Earth, within about 45,000 years, all that oxygen would be absorbed into oxides like iron and sand. Now, it's a good idea to look for life on other planets within the solar system. NASA's launched the Europa Clipper to a moon of Jupiter that looks promising. Titan and Enceladus are also promising sites for life to arise. And Mars may actually have liquid surface water, although this is a highly contentious issue. But if we were to open up our search to the whole Milky Way, the galaxy we live in, there are 100 billion stars. Most of those stars we now know have exoplanets, and many of those exoplanets will be Earth twins, which is to say they'll have exactly the right distance from their host stars for the surface water to be in liquid phase, not frozen into ice and not heated to steam. We tend to believe the water is probably a necessary prerequisite for life to arise on the planet. So what do we need to do this program? Well, we need a really big telescope like the GMT. This is a very faint signal. We need to put it at the best possible site on the surface of the Earth, where the skies are very clear and the stars don't twinkle very much, so we can make really sharp images. And finally, we need a very large and stable spectrograph. Now, what do I mean when I say that? Well, if we imagine a prism to be a spectrograph, it's a primitive spectrograph, and we observe a stellar spectrum, which you see sort of in the bottom bar here. You see the light from the star smeared out from violet all the way through the spectral colors to the red end of the spectrum. But in addition to the smear, we see these dark bands. We call them absorption features. And these are the fingerprints of all the materials that are in the star's atmosphere. And each molecule has its own fingerprint. So when we look at this spectrum and we see, for instance, that band in the middle in the green, that means there's magnesium in the atmosphere. And you see some other lines that match up with iron. That means there's iron in the atmosphere. Might be some calcium, but there is no hydrogen in the atmosphere of this star. Know that just by looking at the spectrum. With this information, we can do things like we can measure the mass of the exoplanet. Is it Earth-like? Can we measure the orbit? Is it in the habitable zone of the host star where water's going to be in liquid phase? And finally, we can search for Earth-like biomarkers. How would we actually do that? Well, the first thing we do is measure the light from the star. And the light from the star will have its own set of fingerprints from materials in its atmosphere. The light, then wait for the planet to go in front of the star, and the light also passes through the atmosphere of the exoplanet and adds its fingerprints to the spectrum. Now, all we have to do is take the light from the star only, subtract it from the star and the exoplanet, and what's left over is the light from the exoplanet. Now, I've made this sound very simple. It's not. It requires a very dedicated and large team of scientists to actually accomplish this subtraction, but we know that it works if we have the right equipment to make the measurements. So let me tell you a little bit about where we are. Here's a picture of the G-CLEF instrument, which has been sliced in the computer-aided design software, photoshopped in pictures of Sagi Ben-Ami, my former instrument scientist, who's now a professor at Weizmann Institute in Israel, and Juliana Garcia Mejia, who is now a fellow at MIT. Just to give you a sense of how big G-CLEF is. First thing you notice about G-CLEF is it has this blue can that it sits in, and that is to make it thermally stable. What we do is we suck all the air out. The same way when you want to keep your coffee warm, you put it in a thermos bottle. You put it in a vacuum container. That vacuum chamber is almost done. It's being built by a vendor in Utah, and it should be at the CFA in about 3 or 4 weeks. Next issue is how we hold all the optics. We have a thing called the optical bench. It's exquisitely engineered for stability by Northrop Grumman Innovation Systems. Was delivered about a year and a half ago, and it's ready for the vacuum chamber when it comes in. We have 2 cameras. We actually split the light in the spectrograph into 2 parts of the spectrum, a blue end and a red end. This is the camera for the red end of the spectrum. Again, exquisitely engineered for high stability and high performance, actually exceeds requirements by a factor of about 5. Then the thing that spreads the light out in the spectrum is a thing called an Echelle grating. Again, the Echelle gratings have to be exquisite. There are 3 of them, and they have to be exquisitely co-aligned. They're aligned on a special material called Zero-Dur, that honey-colored stuff you see that has the lowest coefficient of expansion of any material known to mankind. The really big collimator mirror has been delivered about a year ago. The smaller pupil transfer mirror has also been delivered. Complicated bit of business called a Mahjong mirror, very hard to make, also has been delivered. The dichroic, which splits the blue and the red half of the spectrum up, has been delivered in prototype form by our colleagues in Korea. We have all the lenses for the blue camera, but at this point, we're trying to raise money to build the metal bezels that support the lenses. And finally, just a quick shout out to my colleagues at the Korea Astronomy and Space Sciences Institute, who about a year ago delivered the absolutely critical calibration system for the G-CLEF instrument, and looking forward to future collaborations with them as we go forward. So thanks again for taking the time to listen to me tell you a little bit about the G-CLEF instrument, and I look forward to actually getting to work building it. Thanks so much.
Thank you, Andy. Some of you may have experienced a bit of technical difficulty during this last portion, and we've got that fixed now, so we apologize. Having spent years building instruments myself, I can say this is exactly why we build large telescopes. Every gain in light collecting power, stability, and sensitivity opens doors we didn't even know existed. With G-CLEF, we can move from detecting Earth-like planets to actually measuring them, and perhaps for the first time detecting signs of life beyond our own world. For our next pre-submitted question, we turn to another instrument builder for the Giant Magellan Telescope, Jared Males, an astronomer and principal investigator of the GMagAO-X at the University of Arizona. He will answer a question from Brandon, a journalist at Live Science, about how our telescope's instruments will work in synergy with the James Webb Space Telescope to characterize exoplanet atmospheres and search for potential biosignatures.
Thanks for your question. JWST works at infrared wavelengths, making it perfect for imaging young planets far from their stars. Such planets are still hot and glowing from their own formation. Because space is cold, the thermal background is very low. So observing from space in the infrared is a lot like when you go look at the stars away from the lights of the city. With GMagAO-X, the instrument we're building for the Giant Magellan Telescope, we will be able to take pictures of old planets, which are no longer producing their own heat. We'll study them in the reflected light of their star, the way astronauts see the Earth from the moon. GMT is also nearly 4 times bigger than JWST, and we're designing GMagAO-X to work in visible light. Both of these things will give us much better angular resolution. That means we can detect planets at much smaller separations from their parent stars, reaching habitable zone planets like the Earth. By taking spectra, we'll characterize their atmospheres and compositions, and yes, look for biosignatures. So GMT will both complement and expand on the remarkable work James Webb has already done. Thanks again for the excellent question.
Thank you, Jared. We have another science question from Manisha, a reporter from space.com. She wants to know about some of the unique discoveries the Giant Magellan Telescope will make. To answer this question, we reached out to Gwen Rudie, staff astronomer at Carnegie Science, who specializes in observational studies of distant galaxies.
Thank you for that question. I study galaxies and how they've formed and changed over time to create the wide array of shapes and sizes we see in our nearby universe. We know that galaxies and the stars and planets within them form from vast clouds of gas drawn together by gravity. The largest stars burn brightly and die in tremendous explosions, driving that gas back out in immense winds. But this cycle of gas falling in, forming stars, and being thrown out is not yet understood because this gas is too challenging to see. The Giant Magellan Telescope will let us study galaxies at tremendous distances, which means peering back in time 10 or 11 billion years when they were forming stars the fastest. GMT will revolutionize our understanding by creating the first maps of gas surrounding individual galaxies. And we'll also be able to peer into the hearts of these young galaxies to connect the sites of star birth and death directly to these gas flows. This will be a big clue in answering one of humanity's most basic questions: where we and the galaxy we call home came from. These observations and the questions they'll answer are the ones I'm most excited to study when GMT comes online. But I believe the most remarkable discoveries GMT will make are the ones we haven't even imagined yet. GMT will be new eyes on the universe, and with them, there's no telling what we'll find. Thanks again for that question.
Thank you, Gwen. We have many more audience-submitted science questions that our Chief Scientist, Rebecca Bernstein, will answer at the end of our program, so stick around. Now, we continue our journey, traveling to South Korea to celebrate a major step in international collaboration and funding for the Giant Magellan Telescope. Astronomy drives discovery and our understanding of the universe, but it also fuels innovation beyond the lab. Technologies first developed for telescopes appear in everyday life: imaging sensors in our phones, GPS navigation, advanced medical imaging, and breakthroughs in artificial intelligence and pattern recognition that help us make sense of enormous data sets. This is how curiosity-driven science improves both knowledge and quality of life. But perhaps the most powerful aspect of astronomy is that it transcends borders and politics. When I look at our international map, I see universities, research institutions, industries, and countries working together to build something that no one could achieve alone. One of these partners is in South Korea, whose commitment to the Giant Magellan Telescope has been deep and sustained. It is my honor to introduce a longtime colleague and friend, Byeong-Gon Park, director of the Korea Astronomy and Space Science Institute's Large Telescope Program. He's here to share an important announcement.
오늘 이 뜻깊은 자리에서 발언할 수 있는 기회를 주신 GMTO의 프레지던트 댄 제피 교수님과 관계자 여러분께 감사드립니다. 그리고 오늘 참석하신 모든 분들을 환영합니다. 저는 대한민국의 유일한 국가천문학 연구기관인 한국천문연구원 카시에서 일하고 있는 박병곤이라고 합니다. 저를 잘 모르는 분들을 위해서 제 소개를 간단히 드리자면 저는 대한민국의 대형 광학망원경을 위해서 20년 이상을 일하고 있고 특히 2009년부터는 대한민국을 대표해서 GMTO의 이사회에서 활동하고 있습니다. 거대 마젤란 망원경, 즉 GMT는 세계 과학계에서 매우 중요한 연구시설입니다만 대한민국에게는 특히 중요한 의미가 있습니다. 저는 지금 약 600년 전 조선시대에 만든 천문관측기기인 가니 앞에 서 있습니다. 대한민국의 천문학 역사는 1500년 이상 된 것으로 알려져 있습니다. 하지만 현대적인 의미에서의 천체망원경은 1978년에 운영을 시작한 61cm 망원경이 시초였고 1996년에 1.8m 망원경을 갖추게 되었지만 30년이 지난 지금까지도 이 망원경이 대한민국 국내에서는 가장 큰 망원경입니다. 따라서 대한민국의 천문학자들에게 있어서 대형 광학망원경의 확보는 매우 오래된 수건이었고 2009년에 정부의 결정으로 한국천문연구원이 GMT 사업에 참여하게 된 것은 대한민국 천문학자들의 꿈을 이루기 위한 첫발걸음이라고 말할 수가 있습니다. GMT 참여를 계기로 대한민국의 천문학자들은 GMT 완성 이후를 대비해서 여러 가지 활동들을 활발하게 하고 있습니다. 4m에서 8m에 이르는 중대형 망원경을 이용해서 연구를 하고 있고 GMT 시대의 우수한 연구 인력을 양성하기 위한 노력을 하고 있습니다. GMT 참여를 계기로 한국천문연구원은 텍사스 대학교와 함께 근적외선 고분산 분광기인 아이그린스를 개발했는데 이것은 세계적인 비슷한 기기들 중에서 가장 우수한 성능을 가졌음이 입증되었습니다. 이를 바탕으로 지금은 GMT에서 사용할 적외선 고분산 분광기인 GMT 뉴얼스를 개발하고 있습니다. 그리고 조금 전에 앤디 센초지 박사님께서 말씀하신 것처럼 스미소니언 전문대와 함께 가시광선 초정밀 분광기인 G-CLEF를 개발하고 있는데 이것은 GMT가 완성된 이후에 사용될 최초의 연구용 관측 장비가 될 것입니다. G-CLEF와 GMT 뉴얼스는 각각 가시광선과 적외선 영역에서 별과 행성의 생성, 은하의 진화, 외계 행성의 대기 연구 등 지금까지 볼 수 없었던 탁월한 연구 결과를 만들어낼 것입니다. 카시의 과학자와 엔지니어들은 세계 최고의 성능을 갖출 GMT의 건설에 참여하고 있다는 데에 크게 자부심을 느끼고 있습니다. 저는 GMT가 21세기 세계 과학계에서 가장 중요한 연구 장비가 될 것임을 확신합니다. GMT를 통해서 우리는 지금까지 밝혀지지 않은 암흑물질과 암흑에너지, 우주 최초의 은하 생성, 우주 생명의 기원 등 근원적인 의문의 해결에 한 발짝 더 다가설 수 있을 것입니다. 이 중요한 프로젝트의 성공을 위해서 한국천문연구원은 지금까지 약 1억 달러 이상을 투자해왔습니다. 최근 미국 국립과학재단은 GMT의 건설에 미국 정부의 예산을 투자하기 위한 공식 심사 단계로서 GMT의 최종 설계 단계 진입을 승인했습니다. 저는 오늘 GMT가 최종 설계 단계를 성공적으로 완수할 수 있게 하기 위해서 카시가 추가로 800만 달러를 투자하기로 결정했다는 기쁜 소식을 여러분과 함께하고자 합니다. 올해 6월 한국에서 열릴 GMTO 이사회에서는 이 결정을 공식 발표하면서 파트너 기관들과 함께 경축하는 행사를 가질 것입니다. 이 자리는 GMTO의 과학자와 엔지니어들의 노고를 기리는 자리가 될 것입니다. 저는 GMT에 참여하고 있는 모든 협력기관들이 GMT의 성공을 위한 노력에 더욱더 적극적으로 동참하기를 바랍니다. 새로운 발견의 시대를 여는 세계 최고의 천문대 GMT의 건설에 모두 함께 노력합시다. 감사합니다.
Thank you, Byeong-Gon. His announcement of an additional $8 million in investment underscores our shared global commitment to completing our observatory and unlocking humanity's scientific future. Partners don't commit at this level unless they recognize the scientific impact and technological return. We received many pre-submitted questions about funding and partner access to our observatory. To answer one of them, we turned to Robert Simcoe of MIT, who will explain how individual giving can be transformational for a university or institute seeking to join our consortium and gain observing access to the Giant Magellan Telescope.
Thanks. The question of momentum is a really important one for the project. So to me, momentum consists of making visible progress towards technical or organizational goals that all point towards or culminate somehow in the successful construction of this telescope. Now, this visible progress reflects the summed effort of many dedicated individuals, and there's different groupings of people that are needed to make the project go at different points in its life cycle. Right now, the people working on the Giant Magellan Telescope are being supported by investments either from international partners or by philanthropic gifts, either to the founders or to GMTO. Now, visionary philanthropists have enabled many of the most impactful science discoveries throughout history. This is especially true in astronomy, and we expect that GMT is going to be no exception. But in GMT's case, there's something special, and that's that there's promise that you can leverage private donations by bringing the project to the point where a major public investment can be justified. So for founders like MIT, being part of GMT helps our university remain competitive by keeping us in contact with the most cutting-edge technologies, but it also helps us attract the best talent from around the world. Now, we were able to join the partnership this year through a transformational gift made by Terry and Susan Reagon. And I know that GMT is continuing to engage with like-minded philanthropists and also with foundations to expand the partnership and maintain this momentum that we have as we lead into the construction phase. So thanks again for this question.
Thank you, Rob. We are honored to have MIT join our consortium and are overwhelmingly grateful to the Reagans for their generous gift. Individual giving is just one crucial piece of making the Giant Magellan Telescope a reality. As I'll discuss later, federal funding from the National Science Foundation is also a key part of our consortium strategy. We received a pre-submitted question from John at the University of Louisville, who asked about broader astronomy community access to the telescope by universities outside our partnership. To answer this question, I welcome Taft Armandroff, who is board chair of the Giant Magellan Telescope Consortium and the director of the University of Texas at Austin's McDonald Observatory.
Yeah, that's a really good question, and I appreciate the opportunity to respond to it. Going back to the decadal survey for 2020, the Giant Magellan Telescope, GMT, proposed to that survey that NSF, the National Science Foundation, have a 50% share of GMT, and that observing time be available to the broad U.S. community and be allocated by a time allocation committee or a TAC purely on the basis of scientific merit. And we've had some really great progress working with our colleagues at NSF, and I believe that 50% of the time will be available through NSF, so that'll allow us to engage the broad community around a wide variety of scientific topics and be working on the best proposals addressing those topics competed successfully. In terms of the time that's given out to the private institutions and nations who've contributed resources to building GMT, the scientists at those institutions who earn time through their time allocation process, they'll obviously have collaborators at other institutions. So some of the time that goes to what we call the founders, the institutions that are members of GMT, some of that will end up being in collaborations that represent a wide variety of institutions. So we really see the broad community playing a really major role with this telescope, and lots of astronomers having GMT data working on a wide array of the most important problems that are facing astronomy and astrophysics today.
Thank you, Taft, for answering this important question and for highlighting the role the National Science Foundation plays in providing broader community observing access to the Giant Magellan Telescope. Before we move on to the live Q&A with our Chief Scientist, Rebecca Bernstein, let me share what comes next and what it will take to bring the Giant Magellan Telescope to completion. As some of you know, in June of 2025, the National Science Foundation, the United States government agency that funds ground-based astronomy, officially advanced the Giant Magellan Telescope to its major facilities final design phase. This is one of the final steps in a project must take before it can be considered for federal construction funding. Over the past 5 years, the telescope has passed every independent federally required review, with many of its subcomponents already exceeding benchmarks for technical readiness. These accomplishments have been made possible by our international consortium of 16 universities and research institutions that together have invested more than $1 billion to advance the telescope. These contributions, largely made possible by donors and supporters around the world, have enabled 40% of the telescope's components to be in active fabrication and assembly, turning decades of planning into tangible progress. We now look forward to the next 2 to 5 years. My immediate focus is successfully completing the National Science Foundation's final design phase by mid-2027. This work involves refining detailed designs and prototypes and demonstrating the strong governance and project management required to build and operate a facility of this scale. Along the way, we'll have a midpoint review in September 2026, and will submit construction state proposal in April 2027. In the next step, after the final design phase, we will be to enter the major research equipment and facilities construction program at the National Science Foundation, and to work with Congress to bring this project forward into construction. The Major Research Facilities Program is the same program that provided the funding necessary to build the nation's largest scientific facilities, and it has enabled landmark projects such as the Vera C. Rubin Observatory and the Leadership Class Supercomputer at the University of Texas at Austin, something I helped bring about as Vice President for Research at UT. Pending approval by the NSF and the United States Congress, the Giant Magellan Telescope will enter the construction phase in fiscal year 2028. For the Giant Magellan Telescope, this will mark the beginning of full-scale construction, completing the telescope site and enclosure in Chile, delivering and integrating the mount and mirrors, commissioning the adaptive optics, and preparing first light instruments, leading to first observations in the 2030s. However, federal support alone will not bring the telescope to life. Completing this vision requires a diversified approach. To do this, we will grow philanthropy and individual giving across our partner institutions, as you heard from Byeong-Gon. CASI's additional contribution is the first step. We will expand our consortium, bringing in more resources and added brain power to drive discovery, as you heard from Rob Simcoe earlier when he spoke about MIT's partnership. We will engage industry globally across manufacturing, optics, software, and data, building on partnerships like Ingersoll Machine Tools and their role in manufacturing our telescope mount. And finally, we'll secure long-term federal support to enable sharing the Giant Magellan Telescope with the entire astronomy community. These contributions accelerate schedules, support education and workforce development, and inspire the next generation of scientists and engineers, all while delivering a transformative impact on science, technology, the workforce, and the economy. They also create lasting public engagement through initiatives like the Visitor Center in Coquimbo, which will be announced later this week. The Giant Magellan Telescope will provide access to a tremendously capable, extremely large telescope for our partners and the US and Chilean communities, and provide a set of unique ELT capabilities for international astronomy. With deeper engagement from our existing partners, with growth in our consortium, with effective participation by industry, and with true public-private partnership, together we will bring the Giant Magellan Telescope to life to drive discovery and to foster a sense of wonder for the decades to come. Thank you again for joining me during International Dark Sky Week. I'd now like to welcome Rebecca Bernstein, who will be running our Q&A session.
Thank you, Dan. It's great to be here, and I get to do the fun part today. I'm going to answer questions that were pre-submitted and mix in some of the questions that we got during the live chat today. So I'll get to as many of them as I can. And I'm going to start with a question from Victoria and her 8th grade students at the Doolin Middle School in Tucson. And we got some comments from her just during the chat that they're going to the Keras Mirror Lab this week, where they're going to get a tour of where our 8-meter mirrors are made. So that should be super fun. But Victoria's students ask, how will GMT block the light from a star to study an exoplanet that's orbiting around that star? Now, you heard a few minutes ago from Jared Males about the instrument that he and his team are building to do exactly that. That instrument is called a coronagraph, and it basically works by first you form the sharpest image you possibly can, and then you basically block the center star so that you can see the much fainter planet next to it. Now, the basic idea here is a lot like blocking out the sun so that you can see a faint bird flying in the sky next to it. Now, I've made that sound very simple. It's anything but simple. But the instrument that Jared is building, when combined with GMT, is actually going to be the most sensitive instrument ever made for doing this. Now, it turns out that one of our colleagues has asked a question, he's Nobel laureate John Mather, about a project that he's leading to do essentially the same thing. That project is called a star shade. And in that case, the idea is that a spacecraft would launch a similar mask to block the light of the parent star before it even gets to the Earth's atmosphere. Then a ground-based telescope could work with that blocked image to study the planet next to it. Now, John is asking us if GMT would work with such a star shade, and the answer is absolutely yes. We would love to collaborate with exactly that kind of state-of-the-art development. But until that project is actually launched, we will be using coronagraphs on our own telescope, namely the one that Jared and his team are building. All right, the next question comes from George at New Braunfeld Astronomy Club. He's asking about the prospects for future improvements of adaptive optics after GMT sees first light. Okay, so let me give you a little bit of background first to make sure this answer makes sense. So adaptive optics, or AO, as I'm inevitably going to call it in a second, refers to how we correct the turbulence caused by the Earth's atmosphere. Now, that turbulence is what causes stars to appear blurry to our own eyes. They're not really blurry. What they're doing is jittering. So we need to remove that jitter using state-of-the-art sensors and software that first measure the jitter, and then we use something called deformable mirrors that can actually change their surface thousands of times per second, so that when light reflects off them, the jitter is gone. And when I say it's gone, I mean we can actually reach something called the diffraction limit of the telescope, which is the sharpest image that physics will allow that diameter mirror to make. So our AO system utilizes optics, electronics, detectors, software, all of which are state-of-the-art. So now to actually answer the question, all of the key components that I just mentioned, the software, the electronics, the optics, the deformable mirrors, they're all likely to improve over time. So by upgrading those systems, whenever major improvements come along, we will be able to improve the performance of the telescope. Now that's probably a good place to segue into the next question, which comes from Keath Cooper at space.com. And he's asking about the telescope design itself. He wants to know why we use our 7 large segments, which are 8 meters in diameter, to make our primary mirror surface instead of using hundreds of 1 meter mirrors or 1 meter segments to make up that primary mirror surface. Okay, now to be clear, there are challenges with either solution, but our mirrors have some huge advantages. And in the interest of time, let me cut straight to the most important of those, which is that our 7 primary mirrors can be used with a 7-segment secondary system. And that secondary mirror system, when it's segmented into 1 meter diameter mirrors, those 1 meter diameter secondary mirrors can be deformable. And that is a game changer. So there's more information about that on our website, but let me just give you a sense of what those deformable mirrors look like and do. So the secondary mirrors are complex structures that of electronics and positioning actuators and I've lost the word I'm looking for, but they're complex structures. And the mirror itself is a 2 millimeter thick mirror that's 1 meter in diameter. So 2 millimeters thick, 1 meter in diameter. That's the thin shell of the mirror surface itself. Now, attached to the back are about 700 tiny magnets on each one of those mirrors. They're being pushed and pulled by electromagnetic coils, and that lets them change their shape and actually wiggle thousands of times per second. So again, they take out the atmospheric jitter when light reflects off them. Okay, so one of the reasons we wanted to use these mirrors is because they're actually proven technology. They're a 4th generation design, and the other 3 generations are being used on working telescopes today, and they work beautifully. So again, this AO system, which is right at the heart of this telescope, lets us feed AO-corrected light to any of our instruments. It's extremely efficient, being that it's just right there at the second reflection, and it's very high performance. So that is one of the key advantages of our 7 primary mirror design. Okay, the next question comes from Craig at the Carnegie Institution for Science, and he points out that by the time GMT is complete, the European ELT, or the EELT as we call it, will have been operating for several years. Now, I think what he's getting at here is he's really asking about the impact and the competitiveness of GMT, which is very important, so let me comment on that. The first point I want to make here is that in the last generation of telescopes, there were about 15 of what you'd call that current generation, about 8-meter class telescopes. They all have different strengths, but even when they have overlapping strengths, they're checking each other's results, especially when those are the most interesting and the most dramatic results. So difficult measurements get cross-checked all the time. That's really important. The second point is that all of those telescopes are oversubscribed. So really what I'm saying is that each of the communities that has access to those telescopes wants more time on them, not less. And the last point is that each of those telescopes, and GMT and the European ELT will be no different, are only accessible to the community that built them. So if we want US scientists to be doing science and developing technology and training scientists instead of reading about scientific results that are being done in Europe, we need to have our own facilities. And the last point is, as I've already said, and a few of our earlier speakers have mentioned in response to other questions, GMT will really have capabilities that the European ELT won't have. These are not redundant telescopes. So it would be a huge loss in terms of just discovery space for the US community internationally if we only build one of these ELTs. So GMT is really key to US science and to the science around the globe, and particularly to our partnership. All right, question number 5. Now, we've had several questions about this. Several of them came in live today. So I want to spend a little bit of time addressing one about satellites. So Keath Cooper also asked this, again, from space.com. And so most of these questions are getting at, in different ways, how satellites that are currently being launched will affect GMT and how we're going to deal with them. Okay, so first let me explain what the issue really is. When a satellite is directly in the location where we want to be observing, it can make a bright streak across the image. Now, if that happens, we have to just delete the affected pixels. So essentially, we lose a % of the image, and it makes our observations a tiny bit less efficient. Now, the more sky you're looking at, the more satellites you're going to hit. But GMT's bread and butter is to be looking with a lot of sensitivity and a lot of spatial resolution at smaller areas of the sky, often single objects. So GMT is really not going to be as affected by this as some kinds of telescopes and observations. Now, that said, it's still important, so let me comment a little more. All right, so when is this the biggest problem? It's the biggest problem when satellites that are bright are in the field of view. Satellites are only bright when they're actually lit by the sun. So they're only really bright when they come out of the shadow of the Earth and sunlight hits them directly. The second point is that we actually already have a lot of experience with this kind of problem because our detectors naturally pick up something called cosmic rays. And those cosmic rays leave a bright streak in the detector itself and therefore in our images. And so we have strategies for taking the data and processing the images that can mitigate this effect already. All right, so with all that in mind, of course, we are working with astronomical communities and institutions around the world to help the companies that are launching these satellites to understand how they can have lower impact on astrophysics and astronomical research from the ground. So that includes things like developing paints so that the coating of these satellites are less reflective when they do come out of the shadow of the Earth. We can put them into higher Earth orbit so that they affect our images less, can change their attitude and orientation slightly so that they reflect less light. And finally, the companies can coordinate with us a little just to make it easier for us to avoid those. All right, so I think I have time for just one more question, and that is asked by John, and he's asking, how far north and south will the telescope be able to take images? Okay, that's a great question. Basically, telescopes look from zenith to directly overhead to about 60 degrees over, give or take. Now, GMT will go to about 60 degrees exactly, in fact. Now, what part of the sky you can reach depends on where you are on Earth. So from our location in Chile, and projecting the Earth's coordinates out into space, so you can just think of it like that, we can look from the south pole of the Earth projected into the sky up to about 30 degrees north of our equator. That gives us access to the entire center of our galaxy where the black hole resides and a lot of very interesting science. It gives us access to the rest of our galaxy and a lot of interesting star formation. It gives us access to the nearest, it turns out, nearest potentially habitable planet, Proxima Centaurus b, which Jared was mentioning earlier. And in terms of cosmology, since the universe is homogeneous, we can look in any direction to do cosmology. All right, we have a few more questions, which we'll try to answer in different ways. Maybe we'll put some answers on our website. But just getting on to, I think, closing us out since we're at time. On behalf of the entire GMT team and our international partners, I really want to thank you for joining us today and for all the questions that you sent in, both pre-select, those before the actual event and during our event. And please be sure to join us next year. You'll be able to check in on our progress, and you'll be able to check in on our progress on your own if you sign up for our newsletters and if you follow us on social media, and we'll be sure to invite you to our future events. So with that, I think we're concluding our Giant Magellan Telescope Summit 2026, and we'll see you soon. Thank you so much.